I want to introduce you to Yingzhen Li. And thanks also for coming to give us a lecture. She's going to give us a lecture about Bayesian neural networks. She's a lecturer at the Imperial College London. Has experience, worked at Microsoft Research, at Disney Research as an intern as well, and studied at the University of Cambridge. Did a PhD with a focus on approximate inference, and has worked in many topics related to what we see here in the school: variational inference, different models, Gaussian processes, Bayesian neural networks. So welcome, and thank you.
Okay, thank you very much. Okay, so can everyone hear me well? All right, okay. So yeah, thanks for hanging up. Okay, still for after 3 days of very intensive lecture. So yeah, it's my first time being here in Norway, so I'm very excited. And yeah, I'm going to tell you a little bit about Bayesian neural networks, and especially this is a topic that has been, researched for quite some years. So there are quite a lot of advances there. So I cannot tell you within these 3 hours. So my goal today is basically to give you some sort of the introduction on the basics, and then gives you some, say, hands-on tutorials. So hopefully after that, you can basically code up a simple Bayesian neural network, and if you are interested, you can definitely explore the more advanced versions later. Okay? So, well, I don't think I need to motivate this. Last year I still need to motivate for this, but I don't think this year I need to motivate for deep neural networks being awesome, right? So one of the interesting things that people may actually want to ask is, okay, now deep neural networks has been used to play games, generate amazing text and images, right? Can we actually apply these things to, say, more critical applications like healthcare? Okay, so in fact, around like 7 years ago, 2016, okay, in a summer school, Jeff Hinton basically said this, that deep neural networks are amazing in terms of helping, say, doctors to read the medical images. And he actually predicted at that time that in 5 years, the radiologists will lose their jobs. Okay, so remember this is 7 years ago, and nowadays radiologists are definitely still safe in their job. Okay, and you probably have heard about a lot of hype right now, saying that, okay, ChatGPT and the new things will sort of like create sort of like extinction erase for humankind. So I think that these are hype because they are right now not really applied to these safety critical areas without passing some checks. For example, you can basically use a neural network to read, say, brain scans, and then say, okay, I think there is a tumor in your brain. Okay, but then the doctors will actually ask you, okay, why you think about this? Can you give an explanation, especially whether you are certain about this particular region that the patient has a tumor there? Okay, so it basically means that you need uncertainty estimates, and you need some other robustness properties, right? Because doctors are going to, use these predictions to at least use that as part of the reasoning to base their decision on for the next step treatment. And for treatment, you can have side effects, right? So that basically means that this decision has risk, has potential downsides. So it means that, if we wanted doctors to basically use AI to help decision making, then, the AI cannot just only produce a prediction result, even when they say it has some high accuracy on some standard test data set. No. So you need some other reassurance to the doctors in order for them to trust their result. So using the latest example of, let's say, large language models, right? So there are actually quite a lot of engineering and health and social sector that actually wants to use this model. Okay, so you can imagine that you can use a large language model for reading electronic health records for the patients. right? So the doctors may ask the models to summarize, okay, given this record of the patient, can you summarize, let's say, the condition of the patient and maybe potential health issues that need some attention from me, right? Okay, so large language models potentially could actually give you this summary, right? But apart from this summary, the doctors will actually prefer you to give this summary and then at the same time give a confidence estimate for each of the points, especially when this language model is trying to point out some potential health issues. So similarly, if you go to, let's say, some construction sites, okay, and you know safety is very important in construction sites, and you definitely have these managers on safety just watching at how safe the construction site working condition is, okay? So the safety manager might actually also say, okay, here's the summary of, let's say, the historical construction, say, safety records, and let's say the potential condition right now. Can you maybe help me point out some kind of potential risk that I need to watch out? Okay, so language model can potentially also point you out this some risk, right? But if there is a very long list, right, then the manager will actually want to see which one is more prioritized, and they actually want to see some kind of uncertainty estimate in terms of, okay, how likely this risk is going to be real. Okay. So I hope this gives you some quick motivation in terms of why just outputting the answer is not enough. So this motivates us to use, let the neural network output some other metrics, including uncertainty, and uncertainty will be today's topic, at least this morning's topic. Okay? So, I mean, there are different ways to estimate uncertainty. And in fact, if you look at statistics, there is these two different camps, frequencies and Bayesian. And there are definitely frequencies methods as well. But we are not going to talk about it today. We are going to talk about Bayesian methods because the title is Introduction to Bayesian Neural Networks. Okay? So, hopefully, after 3 days of lectures, you more or less have seen this, right? So I'm just trying to repeat that the Bayes rule is essentially the key concept in uncertainty estimation where you are going to have some prior on the hypothesis, well, which is represented by the parameter theta, right? And then you use some, you have some observed data, and then you're going to update your belief to the posterior belief, P of theta given data. Okay, so this is Bayesian inference, but now theta represents the parameters, let's say the parameters of the neural networks. But in practice, as I motivated before, we are not really trying to look at the uncertainty in parameters. We actually want, for example, the neural network to output some predictions and then give me the corresponding uncertainty estimate for that particular prediction. So this basically means the actual question we want to answer in Bayesian inference is this integral. Okay, so using prediction as an example, right? So you can actually ask in this regression setup, okay, what is the distribution of the prediction for this test output given a test input, right? So in this case, you can basically see this is my test input. And then I get some test output prediction where I can get the mean and also get the standard deviation. Or I mean, if you actually have a distribution, I can actually get a higher order moment for this predicted distribution. So in this particular case, you can see this f function is actually the likelihood when you use the test input. Okay. So in other examples that is not relevant today, people might be interested in looking at the posterior mean, posterior variance, and maybe when they do this kind of decision making, they will actually substitute in a utility function for this f instead of using just the predictive distribution here. But this problem will be the problem that we are going to look at least for the first half of the lecture. Okay? So hopefully this is clear for the general setup, but now I'm going to tell you what exactly is Bayesian neural network. Okay? So let's just imagine that you're going to classify different types of animals. Okay, so usually speaking, you're going to build a neural network, and because this is classification, you're going to use a softmax activation function for the last layer, which means you're going to have a categorical distribution for your model. Okay, so yeah, so this is just very quickly set up. You have multiple layers of neural networks with parameters, theta that collects all the neural network weights and biases. And then a typical deep learning solution is to obtain a point estimate for this neural network parameter theta using maximum likelihood. So in this particular case, for classification, you can imagine that cross-entropy loss is just the negation of the likelihood term. So minimizing the cross-entropy loss is equivalent to maximizing the log likelihood. So once we've got this point estimate using maximum likelihood, and then in prediction, you just plug in this maximum likelihood estimate theta star into your neural network, and then use that particular neural network to do your predictions. So this is a typical deep learning workflow. So in terms of Bayesian methods, though, we have worked with random variables, right? So in this case, the neural network weights theta here, they are no longer deterministic. We are going to view them as random variables. And then we are going to put a prior distribution on theta, let's say a Gaussian prior. Okay? And following our previous mention about Bayes' rule, right, what you need to do, assuming that you can compute it, is you get the posterior, P of theta given D. And then in prediction time, you perform the integration task, right, by using this predictive likelihood as your F function. And then you plug in that to compute what is called Bayesian predictive average distribution. So this is the predictive distribution under the Bayesian setup. Okay, so this is the kind of like the high-level framework. But as I said, you know, I already told you that this needs to be under the assumption that you can compute it. And in practice, you know that apart from, let's say, some very simple models like linear model, the posterior is almost always intractable. So you need some way to compute it. So there are different ways to compute it. Today we are going to focus on approximate inference. So which basically says that, okay, Z posterior is intractable. So we're first going to construct a approximate posterior distribution Q that somehow approximate the Z posterior distribution in some good way. Okay, so if you believe that, then later on, you can basically replace the Z posterior with the Q distribution in your predictive inference procedure. So you can basically see that here we have the Z posterior being replaced by the approximate posterior Q. Okay, but you know, like this P distribution here, right, involves passing this data through a neural network. So even when Q is a Gaussian distribution, let's say, this integral can also be intractable. So what we actually do in practice is we are going to do one more approximation, which is to approximate this expectation term with simple Monte Carlo. So we are going to sample a bunch of weights from the Q distribution, and then for each of the weights, we are going to use that weight to parameterize a neural network, use that neural network to process your data, give them prediction, right? So this is what you can get for each of the network, and then finally you get the average of it. So basically, to summarize, right? So in this Bayesian neural network, you need to actually find a way to approximate the Z posterior. And then in prediction time, you can sample from the approximate posterior, and then use that to form an ensemble. And then use that kind of like the formed ensemble to produce a output. So essentially, let's see how this can work, right? So I will say that the quality of approximate inference is key to the performance of the Bayesian neural network. So let's see why this is the case. Okay, So first, you can think of, as I said, Bayesian neural network as an ensemble, right? But it is actually an ensemble of infinite number of neural networks because you have a distribution over the weights. Okay. So this basically means that you sample from the posterior, you get these samples parameterizing each of the neural networks, shown by little robot here, right? So and then you use that to process your test input, and this will give you a prediction. And in this case, it can correctly classify this image as panda. So now, imagine that you have some test inputs which is out of the training distribution, or even it is an adversarial input. Okay? So in this case, remember that you actually have an ensemble of neural networks where each of the members are sampled from the approximate posterior. So, in this case, you can see that some of the neural networks made wrong predictions. But the important point here is that if you have a diverse solution in this Q distribution, then essentially these different neural networks can disagree with each other. So at the end of the day, it means that even when you made the wrong prediction, because of the disagreement here, you see it, which essentially represents model uncertainty, you can tell that Bayesian neural network in this case is uncertain about its prediction on this out of distribution example. So potentially you can actually look at the uncertainty to see, okay, whether this is a out of distribution example or a normal example that needs your attention. So yeah. So now let's see how would the quality of the Q distribution actually impact on this procedure, right? So the promise here is that if you have an accurate approximate posterior, then it should be able to give you some good uncertainty estimate. But now imagine that your approximate posterior is a very poor approximation to the exact posterior. In particular, it is a very concentrated distribution closer to a delta mass. Okay, so it means that essentially all the members you sample from this approximate posterior is going to be the same neural network. So effectively, you lose the advantage of Bayesian neural network, which means having a distribution of experts that can disagree with each other, because in this case, you basically see they are the same experts. Okay, so they can make wrong predictions. And because they are essentially the same expert, they can make wrong predictions without too much uncertainty telling you. Okay? So this first means that your posterior approximation shouldn't be that narrow as compared with your exact posterior. On the other hand, okay, too flat approximation to the posterior is also bad. Right? Okay, so we said that we want, diverse experts in your random ensemble, but we are not saying that we want any expert. Especially we don't want random guess. Okay? So this basically means, okay, so if your posterior approximation is basically very flat, maybe covering some mode of your exact posterior, but also covering some, low density regions of your exact posterior, then essentially you're including some experts that are not doing well on your data set. And you can basically see that even for the in-distribution inputs, your expert basically gives different answers, cannot agree with each other, so that you actually have low accuracy in this case. So hopefully, via this little example, you can see that the quality of the approximate inference here is actually very key to the performance of Bayesian neural network, because Bayesian neural network itself can be described as a concept, but when you actually compute it, you need approximate inference. Okay, so let's just summarize what we've got so far in terms of the procedures here, okay? So there are a few key steps that you are going to actually use Bayesian neural networks in practice. So the first step is to construct the approximate posterior Q to the exact posterior P of theta given D. Okay, you can use Gaussian distribution, or you can use some other distribution that we can talk about it later. So the second step is you are going to fit this Q distribution to your exact posterior with some methods, and in particular today we are going to focus on variation inference. Hopefully you've heard about this in the last few days. We are going to repeat that, okay, just to make sure that you can remember this very important concept, variation inference, for basically very important concept for probabilistic machine learning in general. Okay, so assuming that you have got this Q distribution from this fitting procedure, then in test time, as we discussed, sample a bunch of experts from your Q distribution and then use them to form an ensemble for prediction. So this is essentially the 3 key steps. Okay, so this is today's agenda. Okay, so I'm going to start from briefly mentioning about how we actually do mean field variation inference for Bayesian neural networks, and then we will have a hands-on demo that you actually code it out yourself. Okay, and then we will have some other case studies to show that how these uncertainty estimates can be used in some interesting tasks. All right. So yeah, Bayes rule, this is our goal. We need to approximate this posterior distribution, and then the posterior distribution by Bayes rule looks like this, right? So you have your prior term, you have your likelihood term, but then you actually have this called marginal likelihood, which means you need to integrate over all these parameters theta. So this integration is intractable, so that's basically why you cannot directly compute the posterior. We said before that we want to use a Q distribution to approximate that, but we need to find some way to measure the distance or the closeness of these two distributions, right? So we are going to do KL divergence. Okay, so this is the KL divergence from Q to P. It is non-symmetric, so that's basically why we mentioned here is the KL divergence from Q to P. And you can see that this is the expectation of the lower density ratio under the Q distribution. Okay, so it is a valid divergence in the sense that when P equals to Q, KL is 0, and then otherwise KL is greater than 0. Okay, so we can use that to measure the similarity between the approximate posterior Q and the exact posterior P. So let's just plug in that and see what happens. Okay, so we just plug in the Q distribution as well as the posterior distribution to compute the KL QP term. So this is just what we've seen before. Okay, but remember that this posterior is intractable. Okay, so we are going to first, again, use Bayes rule, right, to write down what exactly is this inside posterior, and you can see that there is a joint distribution divided by the marginal likelihood. So then you can see that because log of products equals to sum of logs, and also this log marginal likelihood is independent with the Q distribution. Okay, so we are going to move this log marginal likelihood out. Okay, and then only look at the second term. Okay, so the interesting thing here is that, now the second term here includes the Q distribution as well as the joint distribution of the data and the parameter theta. Okay, and then by definition, right, because if you're going to, let's say, use Gaussian prior, and then you can use some other, say, tractable likelihoods like, say, Gaussian likelihood or categorical likelihood, the joint distribution itself is actually tractable. Okay? So this basically means, notice that this part is tractable, and also the log marginal likelihood is a constant with respect to Q. So this means you can effectively ignore this log marginal likelihood term when you optimize the Q distribution. And then instead of minimizing the KL divergence from Q to the posterior, we are going to maximize what is called evidence lower bound. Okay, the evidence lower bound is basically just equivalent to the KL divergence, except that you have a gap of this constant term. Okay, so how to understand this evidence lower bound, right? So basically, you can show here is that KL, right, this KL term equals to the log marginal likelihood, sometimes also called model evidence, minus, this is the elbow, right? So this is the gap here. So because this term is independent of Q, so it's always going to be a constant staying there. And if you push up the elbow, then effectively you're also minimizing this gap, which means you are minimizing the KL divergence. And remember that we said that KL divergence is a valid divergence to measure the similarity between Q distribution and your Z posterior. So this means if you can manage to push up the elbow and then close this gap, then you can get a good approximation or even exact approximation to the Z posterior P. So this is why you want to do variation inference and maximize the evidence lower bound. So pictorially, it's kind of like the idea like this, right? That because the Z posterior is very complicated, we are going to construct a family of simpler distributions like Gaussians. You can imagine this is a set of all Gaussians, or even all factorized Gaussians. And then because the posterior is definitely outside of this simple distribution set, we are going to find the best projection of the Z posterior onto this simpler distribution set. And the way you define this projection is by minimizing the KL divergence, which is equivalent to maximizing the elbow. So in some papers, it actually also called information projection for this minimizing KL procedure. So all this part is basically just similar to what you've heard about in the previous few days, except that we are talking about it in, say, a parameter posterior approximation context. Okay. So in particular, in Bayesian neural networks, often it will be also interesting to rewrite your elbow, right, into the following form. So because we know that log of products equals to sum of logs, that essentially you're going to move around the terms inside the products, okay? And then you can split that into two terms. The first term is often called data fitting term, or sometimes we call it reconstruction error, or the negation of the reconstruction error. So the second term is sometimes also called KL regularizer, assuming that you are going to use a fixed prior. Okay, so this part is actually quite like the usual deep learning laws that you use to train your neural network, except that instead of using deterministic neural network, you are going to use a Bayesian neural network, okay, here to compute the reconstruction loss term. And then the KL term here, the idea here is we want to basically make the Q distribution closer to the prior, right? So you can think about it as regularizing the approximate posterior, especially when using the Gaussian prior, then it's quite close to, let's say, L2 regularizer plus some other variance terms. Okay, so just a very quick recap, right? So these are the 3 steps that you need to perform approximate inference in Bayesian neural networks. And in particular, we are going to do variation inference. And we just have talked about, in principle, how variation inference works, right? But now let's actually see when your model is actually a Bayesian neural network, so which means that theta is the collection of all your weights in the network. Okay, so the first step is to try to define the family of your Q distribution, right? So we know that when you actually use very big neural networks, right, this theta can contain sort of like millions or even close to billions, maybe, in the large language model era, right? Close to billions of parameters. So it needs to be efficient in terms of the approximation. So the first example here is called mean-field Gaussian distribution as your Q distribution, right? So the idea here is we are going to ignore all the correlations, either between the weights, right, within the same layer, or across different layers. Okay. So you can basically see that first, this factorization over layers explains that there will be no correlation of your approximate posterior between the layers. And then within each layer, right, so we are going to also factorize across the connections, which means there will be no correlations between the connections of your weights within the same layer. Same thing happens for your bias term. Okay? So this basically means, okay, so for each individual Gaussians, what you need is to parameterize the mean and the variance. Okay? Parameterizing mean is easy. Okay? The slightly tricky part is actually variance, because you need to ensure that it is a non-negative number, well, a positive number, actually. So it means that you cannot just directly parameterize it with some free-form parameter. Instead, what we usually do is we are going to actually parameterize the logarithm, okay, of the variance, so that it can actually range from, say, negative infinity to plus infinity. Okay, so this will be very friendly to your, code. Okay, there might be some other ways to parameterize it for the variance, but essentially the point here is that because the variance is a positive number, you cannot directly parameterize it with a free-form parameter. You need to apply some transformations. Okay, so you will see that in the later example for the demo. Okay. So we've done the parameterization of the Q distribution, and the next step is to fit the Q distribution, right? So say variational inference, we want to maximize the variational bound, and then you can see that this phi here collects basically all the means and the variance parameter for your Q distribution. So we are going to maximize this, okay? So this is the variational bound, but you can notice that this reconstruction term needs to be computed over the entire data set. Okay? So imagine that you're going to have a lot of data points, and especially a lot of data points of very high dimensional input. So it can be very expensive to basically fit all the data points into your, say, GPU all at the same time, unless you have a lot of GPUs. So instead, the second thing that is very important here is for scalable computation, we actually need to use the idea of stochastic optimization, i.e. stochastic gradient descent. Okay? So the idea is the following. So if you assume that you have, say, ideal assumptions across data points, okay, then essentially this log likelihood term can be rewritten as a sum over each of the individual data likelihood. So this means you can actually use a mini batch of the data points to approximate this sum. So if you use a mini batch, then you need to first compute the average over the data likelihood over this mini batch, and then put back the right scaling. So this is basically, you need to notice that you need to have the right scale here. The scale here is actually very important for Bayesian neural networks, because the idea for Bayesian inference is when you actually have a number of data points goes to infinity, you want your posterior to converge to a point mass. And this kind of concept of, say, large data limit is actually denoted using n. So you do need to have this n term here to make sure that you have the right scale. Okay? Right. Okay. So we have done these stochastic optimization techniques, but we also need to compute these expectation, right? So as we said, right, if you cannot compute the expectation in an exact way, then you just do simple Monte Carlo. because we use Gaussians, right? We use Gaussians, then we can definitely sample from the Gaussian distribution and then perform the empirical average to get this approximation. In particular, if you use Gaussians, then you can also use the reparameterization trick that you probably have seen that in yesterday's deep generative modeling tutorials. It's the same trick, okay? So you can compute the samples of your weights by using the mean plus a scaled version of this standard Gaussian noise, right? And then basically, you plug in this theta into your objective. This will result in the following term for your reconstruction term. And you can see that when you actually perform backprop, right, when you need to differentiate that with respect to, let's say, phi, which is either this or this, then the backpropagation part will basically first compute the gradient with respect to theta, and then according to this reparameterization trick part, compute the gradient of theta with respect to mu or sigma. Okay? So again, reparameterization trick is again very useful for this mean field variation inference in Bayesian neural networks. Okay, so these are just the two key components in the step 2, right? Stochastic approximation for mean batching, and also the reparameterization trick for sampling from Gaussians and then compute the reconstruction term in your elbow. So yeah, if you combine both steps, then this is essentially what you will actually compute at the end for your loss function in your code. And in particular, if you use Gaussian prior, and in this case we use Gaussian posterior, right? Then the KL term also has analytic solutions. So you don't need to worry about it too much. But if you don't have analytic solutions for this KL term, you can also use Monte Carlo techniques to do it. For example, if you use some other non-Gaussian approximations involving, say, normalizing flow or some other things, right? Then you probably want to use Monte Carlo methods to also compute the KL term as well. Okay, so yeah, just to mention that in regression, this likelihood term will just be a Gaussian, like this. And in a classification, it will be a categorical distribution with the logit parameterized by your neural network. And then, yeah, once you train that, this is, I repeat again, that in test time, you just need to sample from the approximate posterior. And in particular, if you use mean field Gaussian, then it's again this reparameterization method that you get the mean plus the scale version of a standard Gaussian noise. So you repeat that multiple times to get different members in your ensemble, and then finally use this ensemble to predict your results. Okay, so I hope this is not too fast in terms of introduction, but we are going to have some hands-on exercise here. Okay, so the idea is the following. Okay, so we are going to spend like 25 minutes on this. Okay, so feel free to take a break or like go to a bathroom if you need, right? But essentially the idea here is go to this website. Okay. And then basically there is this Google Colab notebook with some sort of blocks that contains parts that needs you to fill in. Okay, so in order to do that, you probably want to say save a copy on your side and then start filling in there. So let me see. Okay. All right, okay. So this is what you should see if you can open that website, right? So in the next 25 minutes, so you should go through this part, right? And there is a task called a simple regression task, okay? So go through this part and then stop until here. Okay, so we will talk about this in the next part, but essentially we want to use the next 25 minutes to finish up on here, okay? All right, so hopefully you've got some good break and also some tryout in terms of the very first example, okay? Some of you have already noticed some interesting engineering art going on, okay? So let's just have a look at how this works, right? So yeah, again, thanks of our amazing TAs for answering the questions and also writing down these very nice hints, right? So I said in the lecture, right, that, okay, we are using a Gaussian distribution with some mean and some variance for our proximate posterior. But, you know, the variance there needs to be positive. So you cannot directly parameterize it. You need to actually parameterize some other parameters. We use sort of like these parameters here, and then transform it back to the actual standard deviation. Okay, so let me see how I zoom in on it. Okay, I hope this is big enough. All right. Okay. So you basically see that, okay, so this is the actual free-form parameter that we are going to optimize. So we initialize this thing with some PyTorch-like code, right? And you can basically see here, right? So as I said, I recommend initializing the logarithm of the standard deviation. So this is what we actually what I actually did here, right? So I initialized the log standard deviation with some free-form parameters, and when I actually need to get the standard deviation, right, for this posterior, I take the exponential of it and then do some sort of say numerical control stuff. Okay. So this is probably the first thing. And the second thing here is basically, you know, in the forward pass, right? So the forward pass is actually very, very, very similar to a deterministic neural network, because if you are familiar with, say, PyTorch.n, this library, then this is essentially the PyTorch function for computing the forward pass. But you can see that now for this weight and bias, we are not using the sort of like deterministic weight and bias. We instead sample from the posterior. Yes?
Can you explain why you use this clam function to set it to a minimal value? Because otherwise, is it a problem if we just let it go to 0 at one point due to numerical precision?
So the reason is the following. So we use clamp here just for numerical control, right? You can also do the numerical control even inside here, right? By saying that, oh, this is sort of like the logarithm of the standard deviation shouldn't be too small. There is a sort of like, say negative 100 or negative 1,000, right? That you can do it. So this is just one way to control the numerical stability. So, you know, the reason why you need to control the numerical stability is basically when you have when you can compute KL divergence between two Gaussians, and one of the Gaussians has very small variance, then you will have some troubles in terms of numerical issues. Okay, so that's why you need to do this clamp thing. Okay, so going back to the forward pass here. Right, that it's the same forward pass as the deterministic neural network, except that your weight is going to sample from your distribution, and this is your way to implement the reparametrization trick. So basically just as simple as what we've seen from the equations. Okay? So you probably see from this code that the way I structure this code is basically that I basically just construct a sort of like a mean field version inference linear layer, just like you use n nonlinear when you construct a neural networks with PyTorch code, so that you can just directly call this layer, okay, and then construct how the neural networks in say how many layers you like, how deep you want, what kind of activation function you want. And especially, I think one of the students asked me the question in terms of like, okay, whether you need to use, so say, you know, this Bayesian treatment for any of the layers, right? You can say, oh, I can just say I just want part of the neural networks to be treated in a Bayesian way. Then you can still mix in the usual and nonlinear and this new layer. Okay, so it shouldn't be that difficult. We will talk about it a bit more. Okay, so yeah, so you can basically see that here are our examples. Okay, so in terms of how you actually compute the objective, so this is a regression problem. Okay, so for regression problem, you need to have a Gaussian likelihood. Okay. And if you look at, if you understand how to write down Gaussian likelihood, or if you look at Wikipedia, then you just use that kind of expression to write down your Gaussian likelihood function, which contains a L2 error plus some term that actually tries to counter for the output variance term. And then in the implementation of the elbow with mini batch estimate, remember we said that you need to actually figure out the right scaling for your data reconstruction term in order to have the right scale for your approximate criteria. So this is basically how we do it, right? So we compute the data loss function, basically the reconstruction loss, on a mini batch of data points and then compute the mean. So this is the 1/n part. And then in the loss function, we are going to multiply this NLL with number of data points. So this is the n part. Okay. Remember, you have this n over n term. So this is your mini batch size. And this is your data set size. Okay. Good. Yes?
Maybe I missed it. Why are you multiplying the factor collective divisions? Is it like because sometimes uneven values is weighted?
Right. Okay. So for the beta term, right? So this is an interesting question. So the beta term here is essentially, there are two ways to think about it. So one way is to think about how you can actually change beta during time to basically help your model to fit. Probably when you start to actually play around with different initialization of your variational parameters and different number of training steps, you will actually find that if you initialize your Q distribution with way too big variance, okay, then essentially it will start to underfit. Okay? If you initialize your Q distribution to be sort of like way too narrow, then it will start behave like maximum likelihood. And then if you actually don't add in this KL term, it will start overfitting. Okay? So, so for us, instead of one practical recipe for us is instead of sort of like underfit, right, letting the network underfit, our recommendation is actually you want this variational inference method to overfit first and then regularize it downwards. Okay? So this basically means for us, in practice, we actually going to tune this beta parameter because the KL term is trying to regularize your neural network, right? Imagine that if this beta is very big, right, then it will try to regularize your Q distribution towards a prior which has zero mean and some, say, decently big variance. Okay? So we usually start from sort of like close to maximum likelihood solution and then start to turn on, say, beta term and then tune beta term, make it bigger. So that's the empirical trick.
Interpretation of that, like out to regularization, you have like your weights are inside of some ball, it's like some sort of like space in information space, and they help information area. So the interpretation of that, like some sort of magnitude of the vector.
Okay, right. So there are some other interesting way to understand the elbow, right? Okay, so I'm trying to find a. Okay. Let me write it here. Okay. Let's say negative elbow. Okay. Okay, so this is what we actually implemented, right? So this gentleman is asking me about question about whether this is related to some kind of, say, magnitude projection constraint, right? In fact, you can actually think about this as a constraint optimization problem. Okay, you want to minimize over Q distribution subject to okay? So these two questions, they are equivalent. Effectively, if you can look at this just by looking at Q as your sort of object, as your, say, the argument to optimize, instead of looking at the parameters, then this K term is actually, I think, is convex in terms of Q. So you can actually find there will be a one-to-one correspondence between the beta term you use and these sort of like the regions, epsilon, that you want. So this is just the constraint optimization point of view for elbow. And this applies not only to Bayesian neural networks, it applies basically just to any variation inference methods, let's say even for VAEs. It's also the same idea, okay? But usually speaking, you know, for people who optimize this, they will naturally use Lagrange multiplier method, which just goes back to here, okay? So this is another way to understand this problem. All right, okay. So yeah, so you can see there are some interesting regression tasks here. And then start from initialization because your network knows nothing, right? It will just predict a flat function, okay, and then gives you some uncertainty. Notice that I plot here the total uncertainty and the model uncertainty because remember that you have a distribution over weights, but in your Gaussian likelihood term, you also have the output variance term, okay? So they actually represent different parts of uncertainty here, okay? So after training, you basically tune the elbow term, and then in prediction time, it gives you some answers that looks like this, at least for this run. Okay, so I guess if you actually tried out, you know, as we discussed in terms of playground, if you try out different activation function, you try, let's say, different beta values and also different initialization, you will actually get a different result. Okay, even the number of training iterations will matter. So this is, as I said, right? So there is some kind of empirical art here going on. In terms of, and this is for mean variation inference, in terms of how you actually want to initialize your variational parameters, how are you going to optimize it? Okay? So, but one thing that we notice here is that for those who actually know Gaussian process, okay, so this behavior is definitely looks different from Gaussian process. Because Gaussian process usually will give you something very nice that, you know, Arnold Solling called it a sausage plot. Okay? It basically tells you that you have a very big uncertainty around here and some small uncertainty here and then some big uncertainty here. So roughly speaking, if you, for Gaussian process behavior, So, okay, so your boundary function looks like this, and then we have a bunch of data points. So Gaussian process will actually give you something that maybe looks like, okay. Yeah, so this is the part that looks like a sausage. Okay? But you can basically see that for Bayesian neural networks, it's a, at least for mean field, it's a different behavior. Yes?
Can you explain a little bit what a Gaussian process does? Because I'm not working with it, and then explain why.
Well, you can imagine that Gaussian process, in some sense, is a infinite width Bayesian neural network. You just think about it in that way, that's fine. So Gaussian process is not the focus today, okay? But you just think about it as infinite width neural network. Okay.
Why the uncertainty of the Bayesian neural networks doesn't collapse when you are close to the observations?
Because you have noise. The way I generate this data, the output target is not noiseless. Okay? And in our modeling process, right, we also have this Gaussian likelihood that has this output noise variance term that we actually need to learn. Okay? So, that basically puts some question in terms of like whether, let's say, mean field variation inference is the best method for Bayesian neural network. In fact, it is not. There are quite a lot of, say, empirical results as well as some theoretical study also from us telling you that there are some pitfalls in terms of using mean field variation inference. But mean field variation inference, in my opinion, is sort of like, it's still nice to teach because if you understand how mean field variation inference works in Bayesian neural networks, you can easily extend that to some other methods, and also it is fairly simple to implement.
Sorry, I haven't understood the reason why the uncertainty is so high around the observation. Do we have a reason why this happens? Because it seems like there is so much variance.
Yeah, okay. So, yeah, okay. So, one thing, as I said before, is so first the data is noisy. So the way we generate data is the target is also noisy target. So it means that you actually want some uncertainty there. But also it's also related to how you actually optimize this network, right? If you actually start to say optimize this say mean field variation inference for a very long time, and somehow reach some overfitting case, okay? Then what will happen here is basically you will start to overfit in this region, but because of some theoretical issues that I'm not going to talk about today, you also lose the estimate of uncertainty here. So Gaussian process, which is another class of methods that we are not going to talk about today, can achieve the, at least in regression, can achieve a case where you have sort of like very small uncertainty around the observed data, but still have high uncertainty in between. This is what you can achieve with Gaussian process, but with mean field variation inference neural network, you cannot achieve that. There are some problems with this. Okay, so this example, if you play around for a long enough time, with different initialization and different learning rates or different number of iterations, you actually find that either you get to a place where you are overall uncertain, or you get to a place where you're overall very certain, even in the sort of like the in-between region when you don't have data points. Okay? So, yeah. So this basically means, although, you know, this is easy to implement, and it definitely gives you some uncertainty estimate, as I said, right? So the quality of your Q distribution will be crucial in terms of the final result. So we are going to talk about some other approximate inference method. Okay. All right. Okay, so you've experienced with mean-field variation inference, and we talk about some interesting pitfalls for variation inference. So you naturally ask the question about, okay, whether you want to actually use more complicated Q distributions. Okay, so the hope is that if you use more flexible approximations beyond Gaussians, then potentially you can get a better posterior approximation so that we can solve this problem of mean-field variation inference and get something maybe closer to this GP sausage plot. But the problem here is that, why we actually do variation inference or approximate inference at the first time, right? Because we cannot compute the exact posterior. It is not because the exact posterior itself is not sort of like it's not a well-defined concept. It is a well-defined concept. It's just basically computing it or getting sample from it is way too expensive, so that we want some cheap alternatives. So, in other words, if you want to use more complicated Q distributions in Bayesian neural network context, where you're going to have millions or even close to billions of parameters, remember that, then you naturally incur higher time costs and also a higher memory cost. Okay, and in the era of large language models, you clearly don't want to do that. Okay, so instead, we are going to look at two alternatives. Okay, so there are two alternatives we're going to talk about and then maybe let you experience a little bit. So the first alternative is basically called last layer Bayesian neural networks, where you basically just only use the Bayesian treatment in the last layer, but then you are going to use the full covariance Gaussian approximations instead of just mean-field Gaussian approximation. The other idea is MC dropout. Well, there are some debates in terms of whether this is actually truly Bayesian, but it is actually a simple method to implement. All right. So in terms of last layer Bayesian neural network, it's basically just as I said, right? Only do full covariance Gaussian approximation in the last layer. Essentially, it says that my approximate posterior for the whole network is going to be two parts. For the layers 1 to the second last layer, I'm going to use delta measures. Essentially means it is deterministic. And then for the last layer, I'm going to use a Gaussian, but instead of using diagonal covariance, I'm going to use a full covariance matrix. I mean, you can also use low-rank Gaussian for the last layer if your last layer is super wide. But usually for classification problems, the last layers, we can still somehow afford parameterizing the full covariance matrix. So there are some interesting connection of this idea to Bayesian linear regression, right? So you can think about it as this network is actually doing Bayesian linear regression, but your input to the linear regression part is not your original input x. It's actually the feature of x extracted using the neural network layers from the first layer to the second last layer. Okay, so this explains that until the second last layer, you get some features from your input. And then you pass these features into Bayesian linear regression, and then this will give you the result. Okay? So in other words, if you think about the learning procedure for this, right, then essentially it's only the last layer you have this Bayesian treatment. For the first one to the second last layer, you're actually treating it as some hyperparameters in your model that you're actually going to learn it with approximate maximum likelihood, where I say approximate because you are still maximizing a variational lower bound to it. But essentially, you're going to learn it with close to maximum likelihood estimate. Okay? So last layer Bayesian neural network is cheap in the sense that it doesn't matter how deep your network is. As long as your last layer is not that wide, you can still implement it. Okay? So this is the objective, as I said, the lower bound objective you're going to implement, right? It is the same lower bound objective. You can write essentially in the same form, except that now notice that for the first to the second last layer, you have delta measure, right? And for delta measures, actually, the KL divergence is ill-defined. So in this case, we just ignore them. We just throw away those KL terms and only keep the KL term for the last layer. And then for these parts of the expectation, right, sampling for a delta measure means you just only have one possible case, right? So you use deterministic weight for the first few layers until the second last. And then for the last layer, you sample from this Gaussian distribution. Okay. So this is how last layer Bayesian neural network works. So the other idea, which is sort of like the quite popular in, I would say, in computer vision community, is actually called MC Dropout. Okay. So the idea here is essentially saying that, okay, they are going to define some very interesting Q distribution. Okay. In a way that you can actually sample from this Q distribution very easily, and also make the KL term that somehow looks like the L2 regulator. Okay, it's actually quite an interesting method. So let's see how it actually works, right? So it is still optimizing the elbow, but in their way, they can actually write it down as sort of like the error term, where in training time you run dropout, and also the L2 regulator for your weights. Okay, but then so it means that in training time it just run in the same way as dropout. But in test time, you also run multiple forward paths with dropout to basically get an ensemble and then get the output. So the actual Q distribution for this dropout method actually looks like this. Okay, so remember that dropout, usually speaking, is trying to drop out the output unit, right? Okay, so you drop some output units to get the actual result from dropout. And remember that how you actually get the dropout, get the output unit, right? You get this linear transformation of the input plus some, say, element-wise nonlinearity. So now if you look at the linear transformation, right, then you notice that it is essentially the same thing as dropping some rows from the weights. If you drop some rows from the weights, and by this notation of weights times input, right, you are essentially also just dropping out some corresponding output unit. Okay? Effectively, this basically means that the dropout procedure implicitly defines a kind of mixture of two delta Q distribution, where one of the delta measure locates around 0, and another delta measure locates around your neural parameters. And this pattern is your dropout rate. Okay, so it is a funny approximation, to be honest. Okay, but this is how you can view dropout in a way like doing some posterior approximations with mixture of two delta distributions. Okay, so notice that here we are using this notation of W times X. I think in PyTorch implementation, they actually use the notation of X times W transpose. So there are some differences in terms of implementation, but bear with me. So yeah, and essentially if you use this mixture of two Gaussians and then make, let's say, the variance close to 0, then what the original paper here shows that the KL term that you need to compute will basically, can be efficiently approximated by the L2 error on your weights, this mean parameter. So that's basically why, this paper discussed that how you can basically just do map plus dropout during training, and then in test time also do dropout in order to get this uncertainty out. Okay, so we probably spend like 10 minutes or so, right? So, okay, so there are some other examples here, okay? So this session is called using other Q distributions, okay? So I think the last layer Bayesian neural network is a bit complicated, but you can at least implement the dropout part, Okay, let's spend 10 minutes on this, and then you play around, and then you can compare this result with the previous mean field version inference result. So in the interest of time, we can have a look at the MC Dropout method, because that's the part that you have tried some implementation, right? So dropout is actually not too difficult to implement, right, in terms of how you do it. But the interesting thing here is that I mentioned about different versions of dropout. Okay, so we can see that from the previous presentation, right, there are two views, right? So one is this dropping unit view of dropout. Another view is the dropping function, so dropping weight view. And this is the implementation. I mean, so there is no need to look at it right now. So the tutorial answers will be shared. Okay, you can look at that later. But the reason why we are interested in two different implementations of dropout is regarding to the plots of the functions. Okay, so we fit a MC dropout network, and if in test time, okay, so this is what I actually got result, okay. So in test time, I run this MC dropout during test time, and then I use this dropout weight node mode, because I set dropout weight equals to false, and this is the result you get. So first, you get maybe a nicer looking behavior of the uncertainty that gets something, you know, like going wider and then going narrower, these kind of things closer to source report. But the interesting thing here is that you see some wiggling stuff. Okay? So this is not because the sort of like the posterior itself has some problem. It is because how you actually compute it in test time. So let's just try again, right? So if you do, let's say, use the dropout weight mode. Okay, you see the same plot. And then, but you see a much smoother plot. Can you speak a little bit louder? Yeah, okay. Yeah, okay. So this is the part of dropping out the unit. Okay, if you're going to implement the dropout weight part, then you're going to actually drop the rows or columns, depending on how you actually what you actually use, WX or XW, okay, in weights, and then multiply it with your input. So this is two different modes, okay? And you see that if you do the actually implement the drop weight part, you can actually get back to a smooth function. So the reason is the following. If you implement these drop weights, and then after dropping weights, you pass in a mini batch of data points, then essentially it means that all these data points, they are going to use the same network, because they are going to use the same sort of like mask out weights so that they are consistent. But if you actually do the dropout node or dropout output unit way, right, then essentially the way people implement dropout here is that you're going to probably drop out different units for different input data points. Effectively, it means that when you drop out different units in different data points, you are using different weight samples for different data points. And effectively, it also means that for different data points, you're actually evaluating different functions in your posterior. So in that sense, okay, you cannot look at sort of like, say, the two neighboring two neighboring data points and their values to be coming from the same function. They are actually coming from different functions, and that's basically why you see these interesting wiggly things. Yes?
Can you explain again the difference between the total and model answer?
Okay, so we will talk about that a bit more in the classification part, but the model uncertainty is basically coming from the fact that the model is uncertain about the things that it hasn't seen before. The data uncertainty is the thing that you cannot reduce, right? Just like you flip coins. right? Even when you know the point is fair with absolute confidence, you cannot predict the next coin flip outcome because that particular coin flip itself is also a random event. Okay? So that is the data uncertainty that you cannot reduce. Okay? And in Bayesian neural network, we usually say total uncertainty equals to model uncertainty plus data uncertainty, or in other words, epistemic uncertainty plus aleatoric uncertainty. So that's basically why you can see this plot here. Okay? So the interesting bit here is you can probably see that we are using, say, homogeneous noise variables for the output noise. But then for the model uncertainty, right, it is actually contracting here because it has a lot of data points. But because, as I said before, you have we construct these data sets using some noisy output, which means that the data itself actually has its own sort of like data uncertainty, so you can still represent it with the output noise part. Okay. Mm-hmm.
The plot that you showed before, when the drop weight is false. So we are not using the dropout proof that we adapted to the variational inference. What do we use that?
Well, it's not like adapted to variational inference. It's the same way, but it's basically just how you actually sample from Q. Okay? So the drop weight method is basically you really compute these weights by dropping some rows. Okay? The drop unit thing is basically saying that, okay, I'm not going to explicitly do that. Instead, I'm still going to compute this, say, the weights coming from my input and then just drop the output unit. They are equivalent. But I'm just saying that in test time, when you actually want to plot how it looks like in the prediction time, there will be some differences in terms of whether you use this drop weight mode or drop unit mode, because it will relate to whether you are using the same weights to evaluate all the data points or not. Yeah, just to run it again. Okay, so qualitatively, the uncertainty still looks pretty similar, but you see this interesting wiggly thing, okay? Right, okay, so let's see how much time we have and can go through how much thing. Okay, let's just see. Okay, so we can talk about a little bit about this one application that might be interesting for you, which is Bayesian optimization. Okay, so imagine you want to solve the following task. You have some function f0 that you actually want to minimize. You want to find the minimum of this function. The interesting thing here is that you don't actually know this function. Okay, right? If you actually know this function, you can actually just apply gradient descent, Newton's method, whatever your favorite optimization method. But if you actually don't know this function, what can you do? Right? So in this case, if we assume that we don't know the form of the function, but we can actually get some noisy values from a black box, okay, from this, then we can do something with, say, machine learning and Bayesian neural networks. Okay? So the very first idea for this is basically, okay, so since I can simulate a data set from this black box, I can perhaps feed the neural network to this data set and then use this neural network as a proxy to this ground truth function f0, and then I run gradient descent there. Okay, so this is the very first idea. Simple, but definitely makes sense, right? But the interesting question here will basically be, how many data points you actually need to query from this black box in order to achieve a good fit of this ground truth function f0. So that's the first question, right? The second question here is basically, you are not considering the uncertainty at unseen locations, which basically means that for example, for the functions between this data point and this data point, right? You have a lot of different possibilities, and in particular, if you have a neural network that actually overfits to a severe degree, then it can have some sort of interesting jumps here that would definitely affect your optimization procedure with gradient descent or with some other methods. Okay? So in summary, this idea is valid, but you don't actually know how many data points you need to collect in order to have a sort of like faithful fit to the ground truth function, and you don't actually know how would the function behave in this gap part. Okay? So we want to counter for these 2 points. So that's basically why we do what is called Bayesian optimization. Okay. So Bayesian optimization is still kind of like the same principle, but it's a modification of idea 1. We are still trying to use a model as a surrogate function to fit to the ground truth function, which comes from a black box. But at the same time, we are going to have some uncertainty estimate at the location that we haven't seen. Okay, so in this figure, you can basically see that I'm showing the ground truth function in this black curve. And then if I'm using a Bayesian neural network like this, right, then I will get a fit with some mean that looks like this and some uncertainty estimate here. Okay. And then based on my fit and also my uncertainty, I can design a acquisition function, okay, to tell me, okay, so I've seen the collection of data and I have my best guess. I want to improve my guess. Can you give me the next data point to help me, right? And I actually want to sort of like get as I don't want to get too many queries. I want to use the least number of queries as possible from the black box to be able to finish the optimization. Okay, so this means the design of the acquisition function will be very key. Okay, so once you've got this acquisition function, then you propose a new query point x star, and then you use this new query point, right, to the black box. The black box will give you back the new observation, right? And then together with all the previous observation, right, you use this new data set again to adjust your Bayesian neural network's estimate for this ground truth function, and then you continue this loop. So the advantage of Bayesian optimization is basically, first, you have uncertainty estimates on the function behavior that you have here. This will give you some very useful information to design this acquisition function. Second, the idea of using acquisition function, right, is to basically just make your query efficient. You don't want to submit random data points to the black box. You want to sort of like cleverly choose the query data point to your black box, and then get to the best result as fast as possible. This is especially useful when your black box is very expensive. Imagine that your black box is going to be some sort of, say, chemistry experiment, biology experiment, or in the machine learning context, let's say your X is the hyperparameters of your neural network, let's say number of layers, or number of, say, the hidden layer size, or some, say, learning rate, this kind of thing, right? And your black box there is going to be one episode of training. Okay, so it means that this black box can be very expensive, and in that case, it is certainly very sort of like reasonable to minimize the number of queries to this black box. Okay, so we talk about the advantage of Bayesian optimization, but how you actually do that, right? So the key here is to design what is called acquisition function, this A term. And the very simple acquisition function is called upper confidence bound. So the idea here is the following, right? So you get the mean function out from your model, in this case, a Bayesian neural network. If you use some other models like Gaussian process, it will just be the mean of the Gaussian process, okay? And then if your model can also give you a standard deviation estimate for your outputs, like this sigma x term, okay? Then you basically just reweight that with this beta term and then combine all of them. So in Bayesian neural network context, so essentially it means that in test time, we sample a bunch of experts from the Q distribution, use these experts to compute the mean function and the standard deviation function, okay, from there, right? Okay, so this is the mean function, this blue curve. And then there are some variance function there. And then with this beta term, I can sum them up to form the actual acquisition function, which is shown in green curve here. Okay? So the idea is the following, right? So this beta term will help you to trade off between exploration and exploitation. So imagine that if you have beta equals to 0, this basically means that you are only going to look at this mean function. And from the current fit, this mean function tells you, okay, I need to collect data point here. Okay? So this is one direction. So unfortunately, we don't have too much time left, but we can very quickly go through the classification case. And then in this case, we can talk a little bit about the difference between model uncertainty and data uncertainty, or in other words, epistemic uncertainty and aleatory uncertainty, if you prefer that name. Okay? So, we spent quite some time to talk about regression examples, right? But definitely, for sure, there are a lot of deep learning applications that frame as classification, like classifying images, right? Detecting anomalies, and also like in language modeling, effectively, they are also doing classification, but just over the entire corpus. Okay? So, yeah, okay. So, in the very beginning, when we motivate Bayesian neural networks and the approximate inference methods, we talk a little bit about all the case and also adversarial samples, right? And there is this hypothesis that maybe having some uncertainty estimate and using Bayesian neural networks can help alleviate the problem of adversarial sort of like example weakness for your neural network. So here's the hypothesis, right? So adversarial examples are usually regarded as OOD data, or at least you want it to be OOD data, okay? And our hope is that if the approximate posterior for your Bayesian neural network contains some diverse experts, right, then your Bayesian neural network results will be uncertain on the predictions, right, for these adversarial samples, okay? So then the idea here is that, okay, you probably can use these uncertainty measures as a way to indicate, okay, whether I have this example is an out of distribution example or in distribution example. So that's the idea. Okay. So let's talk a little bit about this uncertainty thing. So previously in the notebook, you've probably seen that we plot both the total uncertainty and the model uncertainty. I mean, model uncertainty is the same term as epistemic uncertainty, and data uncertainty is the same term as aleatory uncertainty. Okay? So there are different ways to decompose uncertainty, but one of the main stream method here is basically say the total uncertainty is the sum of model uncertainty and data uncertainty. So this model uncertainty or epistemic uncertainty comes from the fact that the model lacks knowledge, right? For example, if you have a regression problem with some inputs, then between the gaps, when you have no inputs, the model just hasn't seen any data point, so it doesn't know. So the uncertainty here will basically just reflect that it doesn't know about the behavior of the function in that region. Okay? So the aleatory one is basically about, okay, if my observation data is noisy, right? And I want my neural network to model the noiseless result. For example, in regression, right, we usually say that Y is a noisy target, and your neural network usually only gives you the noiseless target. So you still need to counter for this noise in your data, right? And this needs to be modeled via data uncertainty. It is due to the inherent stochasticity in data, and this is non-reducible. So the example for this is very simple. Imagine you are flipping a coin. Okay? So model uncertainty question is basically just asking you the question, you know, how much do I believe the coin is fair? So it means that if you keep on flipping the same coin many, many times, and then look at, roughly speaking, say the percentage of heads and the percentage of tails, this will give you an estimate about whether this coin is fair, and your confidence on this answer will increase when you continue flipping the coins. Right? So this is basically explains the model uncertainty reduces when you have more and more data. But even so, even when you have a flow, even have you have sort of like a flip the coin for nearly infinite amount of times, you still cannot predict the next flip outcome. This is because inherently coin flipping has this randomness, right, in each of the flipping process. So even if I tell you, okay, I'm absolutely confident, 100% sure that the coin is sort of like fair, or let's say unfair with, let's say, a very high skew towards heads, right? Then for the next coin flip, I still cannot say for certain that the next coin flip result will be heads. Okay? So this is the data uncertainty that is irreducible. Okay? Yes? That's an interesting question. Okay, so the question here is whether you can actually detect whether there are some difference between them. So I would say it's actually very difficult. Usually, in real-world data, we usually assume that both of these things exist. But there are some cases that you can actually differentiate them. So, for example, in medical imaging, right? Usually, we ask the experts to annotate the medical images, right? And then gives you some sort of segmentation results or labeling results, right? And usually, you actually have multiple experts to look at the same image. If you believe those experts, they come from a sort of like same training background, roughly speaking, they are the same experts, right? Then essentially, you are trying to produce, say, different Ys for the same X. So this will actually tell you very explicitly about the data uncertainty, because you view those experts as roughly the same experts. Essentially, you are repeating multiple draws of the label given the same input. So in that case, that will be very clear. But mostly, I think in most of the cases, we don't really have sort of like multiple labels measured for the same data point. So that would be very difficult. But in certain cases like medical imaging, you probably can have a more sort of like clearer separation of the two. Yes?
So it's possible for models to capture those data.
Okay, so let me say that again, right? So okay, so I'm just saying that it is very difficult to have a suitable data set explicitly engineered towards separating epistemic uncertainty and aleatorial uncertainty. However, if you make some assumptions, then you can still do it. So for example, if you made the assumption that let's say in regression case, right, your output noise are going to have the same variance all the way through for any location, right? Then you can still estimate this using the Bayesian neural network method or some other sort of like Bayesian inference methods. And in that case, the model uncertainty will be represented by the uncertainty in the parameters, and the data uncertainty will be represented by this sigma term. However, if you talk about, say, okay, heteroscedastic noise, in that case, yeah, you can still get some uncertainty estimate for the aleatory one. The question will be whether you trust them. Because we usually assume that you can only measure one output given one input. And in heteroscedastic case, you're going to have your variance also, it depends on your input. Okay, so then will be the question whether you actually trust that result. In general, right, so I would say there are many of these calibration methods, especially the frequentist method. Okay, frequentist methods basically say, okay, I'm going to use a validation data set, okay, to calibrate my uncertainty estimate. But unless you have this label noise setter, as I said before, really have some sort of like nearly identical experts labeling the same image multiple times. Otherwise, these calibration procedures, they mainly calibrate for the total uncertainty. So that is an interesting kind of say comparison between sort of like the calibration methods, the frequentist methods versus Bayesian methods, where we explicitly talk about the trade-off here. Okay, so let's see how we actually compute these things, right? In quantitative metrics. Okay, so in classification, right? Let's imagine that you have, let's say, C5 data set, 10 class, right? Then your outputs will be a categorical distribution representing the probability of different class, right? And for measuring the uncertainty of your categorical distribution, right? A natural choice here will be just to use entropy. Okay, so I hope this entropy expression is clear to you because it is very, very closely related to KR divergence. Okay, so KR divergence is sometimes also called the relative entropy. Okay, so essentially, if you have high entropy here, right, then it basically means that you basically just get random guess. Each of the class has basically the same probability, okay, under your prediction. So this is the high entropy case. So you can basically verify yourself. This when you want to have the highest entropy, you need to basically have a uniform distribution across different class. Okay. So when you have low entropy, which means you have low uncertainty, and especially when entropy here goes to 0, essentially what will happen is that your probability mass will be concentrated around one class. So this is the case that you have a big mass for one particular class and some small amount of probability mass for some other classes. And in this case, this corresponds to a low entropy setup. And if your entropy goes to 0, then essentially this probability will all go to 0, and except for one particular class, that will give you probability 1. Okay, so given this behavior of entropy, so it is quite natural to think about entropy as an uncertainty measure. Higher entropy means you have higher uncertainty. Lower entropy means you have lower uncertainty. Okay. So let's think about how we actually compute this, right? So remember that this entropy is defined in the output space, right? You have a categorical distribution to tell you the probability of each class. So in prediction time, for Bayesian neural networks, we will do a Bayesian predictive average, right? Which means we get the posterior, or in other words, the approximate posterior here, and then perform the Bayesian model averaging to get a prediction. So we are interested in this predictive distribution and its entropy. Okay, so this is essentially the entropy we're going to compute. Okay, so interesting enough, you can actually decompose this entropy or total entropy of the predicted distribution as a sum of conditional entropy under the posterior plus a mutual information term. Okay, so don't worry if you don't see how this can be done. But essentially, this is just using the idea of basically manipulating the entropy equations. Okay, so but the interesting thing to understand here is trying to understand what these two terms really means. Okay. Anyway, so just to say that how we actually compute this thing in practice, right? So because we are using Monte Carlo average, right, to approximate the Bayesian predictive distribution, so this also means that you can use this approximated predictive distribution to compute your total entropy. So this is actually how you actually compute it in practice. You get the ensemble, you use the ensemble to get the Bayesian predictive distribution, and then you use that distribution to compute your total entropy. Now, in terms of the conditional entropy, right, for the aleatory one, right, so we are interested in computing the entropy for each of the neural network prediction, and then average it over the posterior. And in practice, what we are going to do is we are going to, again, get these experts. For each of the experts, you compute the entropy, and then you average over it. Okay, so this is called, say, the conditional entropy, because it is conditioned on a particular neural network theta. Okay, and why this is called aleatory uncertainty, right? So remember that in deterministic neural networks, right, when you don't have any uncertainty in your weights, right? So in regression, you still have this output variance parameter that represents the amount of noise you believe in data. And also in classification, you also have this softmax in the output that tells you that you need to parameterize the probability, right? So that basically means that for each of the neural network, right, deterministic neural network, you're still trying to measure some kind of uncertainty, and that is the data uncertainty. So this term, average, is basically just saying that on average across all my experts, what's my estimate on average the data uncertainty from each of the network. Okay? So the mutual information, how you actually compute it. So in practice, we don't actually compute it using the mutual information formula, but we basically just use, let's say, the total entropy here, and then subtract it with the conditional entropy, and this they are all using this Monte Carlo estimate. Okay, so the only difference is whether you perform this average before you compute the entropy or after you compute the entropy. Okay, so the interesting thing here is you can also rewrite the mutual information term, okay, at least if you assume you can do exact inference, in this way. Okay, so don't worry if you don't understand how this can be done, but the important point to notice here is the difference between these two distributions, right? So they all have the same training data, right? But in this first argument here, you're actually looking at a training data set that is augmented by a new pair of input-output. Okay, here you only look at the original data set. Okay, so the K-outer is telling you that the difference between the two posteriors after you've seen a new set of a new data point. Okay. And then you can see this, you need to also compute it on average, right? So this basically tells you, okay, what the model thinks about the posterior is going to change, right? What the model thinks, because this is under expectation over my model, okay? How the posterior is going to change if I add new observation at location X. This is represented by KL term here. Okay? So this essentially gives you some idea about this, epistemic uncertainty, right? Okay, if, for example, this mutual information is high, then essentially it means that, roughly speaking, on average, this KR term is high, right? Then it tells you that, okay, oh, this updated posterior will be very different from the current posterior. And if your current posterior here has sort of like some high uncertainty, right, then to make this updated posterior very different, then you need to sort of say contract the uncertainty estimate. So it tells you, oh, if I actually add in these data points, I can actually reduce uncertainty around this region. So this is how it means by using mutual information to sort of like represent the model uncertainty. Okay, so we probably don't have time to do that, but let me just quickly show you an example here. You can also run this code yourself and then see what you think about it. Okay. So the idea here is we are going to do some attacks, okay, on Bayesian neural networks with different inference methods, but then trained on NNIS. Okay, so these are NNIS digits, right? And we are going to perform one type of attacks called projective gradient descent, which is one of the state of the art. Still the state of the art, even after 5 years, okay, in terms of attacks, okay? So you can actually adjust the attack strength, right, to see to what extent you can break the Bayesian neural network in terms of making sort of like wrong predictions, right? So for example, you can see here, this thing shows, this is the classification result for the clean one, and this is the classification result after you add in the noise, right? So when you add in a small amount of noise, so I think this method is still fine because we are using a very powerful approximate inference method, which is a combination of ensemble methods and also mean field variation inference. By the way, so there was a near-east competition 2 years ago on Bayesian deep learning in terms of evaluating approximate inference, and the winning solution is a combination of deep ensemble and mean field variation inference. Okay, so we are basically just trying to use the best method as possible. Okay, so now with some small amount of noise that you probably cannot see, I cannot see either. Okay, it can still give you pretty good and robust result. Okay, so when you start to increase the strength, okay, so yeah, so I think this is still fine. And then you can see start from here. You can probably, I'm not sure whether you can see some difference, but it starts to get worse. Okay, starts to fool the network. Okay, if you look at that, so we are basically just adding more noise, right? Until some point. Okay, so you can still see the digits, but you can probably also see a bit of distortion around, right? Okay, so this network starts to get fooled. Okay, so this is how these adversarial samples work in this. But as we said, right, our promise here is we want to use uncertainty to see whether we can detect them. Okay, so this is what we did. Okay, let me just scroll down to the last result. Okay. So, okay, some interesting result here. Okay, so what we did here is basically we compute different types of uncertainty, the total uncertainty and the sort of like the conditional entropy, which is the data one, and the mutual information, which is the model one. Okay, and then we use that to basically as a metric for adversarial sample detection. And the way we do that is to set a threshold in a way that you achieve the false positive rates smaller than 5%. Okay? And then for the data points that has uncertainty higher than that threshold, we basically just say that it is an sort of like out of distribution sample. Okay? And then you can look at this basically the true positive rate, right, to see how it actually performs. Okay? So the interesting thing here is basically with this uncertainty estimate, okay, here, especially I think using this total uncertainty and also the conditional entropy here, you can see there is an increase of the true positive rates in terms of detecting adversarial samples when you increase the strength. Okay. The interesting thing here is you see some decrease. That's the thing that I'm not exactly sure, but you can still detect it decently. So you can probably also see a gap between the total uncertainty or conditional uncertainty results and the mutual information one. So this also says that within this method, maybe you might not have very diverse experts, but rather each of the experts just think that, you know, these examples, when you have very strong strength of the attack that looks like this, they are just way out of distribution. Each of the models are thinking about it in the same way. That explains why, for all the models, the data uncertainty is high. They are all kind of agree that they are all uncertain. Okay. So yeah. So in the interest of time, so I'm going to very quickly summarize what we've talked about today, right? But this classification kind of tutorial is also online, okay? So you can play around with it, and also the answers will also be online, okay? So let me quickly mention about some applications. Some possible applications right now, okay? So, I mean, you can also apply this thing to image segmentation, right? Because ultimately, image segmentation is a classification task on pixels. Okay? So it basically says, okay, I can also put a Bayesian neural network on this image segmentation problem, and especially this paper, they applied a dropout, MC Dropout, to this problem for image segmentation. And you can basically see some interesting result that in terms of aleatory uncertainty, right, they kind of detect the edges, which makes sense, right, that usually the segmentation around the edges are the place that usually you are uncertain. And for different data points, they will definitely have different results. So, but the interesting thing here is they have some also epistemic uncertainty plot, and in particular, they highlight this region. Okay, so I checked with these two authors. They basically say that this is the part that in their sort of data collected in Cambridge. Okay, that is not often seen. That looks like this. Okay, so that's basically why they can see some epistemic uncertainty. Okay, similar things, you can also do that with medical imaging. Okay, so this is the result for super resolution for medical imaging data. Okay, so you have a low resolution imaging scan there, and then you actually want to make a high resolution for it. But this is an ill-defined problem, right? Okay. So because you want to basically enhance the quality by injecting, or interpolating the pixel values for these high resolution versions. So there will be some uncertainty there. Okay. So this is the case that you have some interesting results that they are trying to use some different path in the neural network to estimate the mean and estimate the variance, and they have some dropout method. But at the end of the day, what they've got here is given this low resolution image, and they can get some sort of super resolution results, they can produce what they call intrinsic uncertainty, which is essentially the model uncertainty. And this parameter does not mean neural network parameter, okay? This is not the same meaning. It's some parameters in the medical setup, okay? But essentially, I think what they are showing here is their uncertainty map here highlights this region, okay? And from my chat with these authors, they basically say this is the region that has the tumor, okay, inside the brain, okay? So that needs to be taken care of. So some other things that you can also do, one thing is that you can also apply Bayesian neural networks to continual learning. So this is something actually related to the prior, right? So we mentioned about Bayesian neural networks about, say, approximate inference, but there is another component, which is prior. We often use Gaussian prior for that, right? But that is only for one task. Now imagine you have a sequence of tasks. Okay, you have a sequence of tasks that after you learn how to classify between cats and dogs, you later on want to maybe learn how to classify between dogs and monkeys and owls, or something like that. Okay, so how can you sort of like use the previous knowledge that you've learned, right, from cats and dogs, to help you classify dogs and monkeys, and at the same time you want to make sure that your network doesn't forget how to classify between cats and dogs. So this is a problem of continuous learning. Learn a sequence of tasks sequentially without forgetting the previous ones. Okay? So in fact, the Bayesian framework also has this nice thing about called online Bayesian inference, in the sense that you can use the posterior of the previous task as the prior for your current task. Right? And after the current task comes in, you update your posterior, get your current posterior, and then use your current posterior as the prior for the next task. You just keep on doing this, okay? So the theoretical framework from Bayesian methods is definitely sound in terms of this online sort of like posterior update, initializing prior again and update posterior again, this kind of thing, right? But in practice, you need to actually compute it. Comes back to the computation problem. So instead, what we are doing here is basically saying, okay, in all these sort of like places in this online framework when you need the exact posterior, just replace that with the approximate posterior. So it basically says that the previous task approximate posterior will be your current task prior, and then you use your current task to get a current task approximate posterior QT. And then you use this QT as your next task prior. So it's essentially just the online Bayesian inference framework, except that you are using approximate inference. So there are, starting from this work, Variational continuous learning, there are quite a lot of work that trying to investigate this, say, approximate Bayesian inference in the context of continuous learning. So there are quite a lot of interesting work there. Yes? Okay, so here's the question, right? So the theoretical framework, okay, so assuming that you can compute exact posterior. Okay, let's assume that. Okay, because the exact posterior, okay, I'm trying to find it. Okay, so the exact posterior at time t, this is your exact posterior at time t, right? So when you're at time t plus 1, right, then your posterior at time t plus 1, okay, let's just leave it open first, is something that is proportional to your next, the data set's likelihood, and your prior, where we already said that you are going to use the previous data set. Okay? So from Bayes' rule, this tells you what is the feeling here, right? This is dt and dt plus 1. Okay? So ultimately, if you can do exact inference, actually this should be 1 to t. And then this thing will actually become 1 to t plus 1. It means that under exact posterior inference, it naturally just remember all the previous tasks. However, in practice, right, you need approximation, and the question here is whether this queued approximation can somehow, be accurate approximation to this exact posterior, which actually remember all the tasks. Okay, so I think in practice, apart from this variational bound, there will be some other techniques to help make this sort of like QT distribution closer to the exact posterior, which really just remember all the tasks. Okay. So the ideas include, for example, like call set or replay. That are the sort of like the very usual techniques that people use. in continuous learning. But also, if you look at the k-alter itself, right? If you somehow believe that qt-1 contains the previous task information, right? Then this k-alter will also regularize your network towards sort of like not forgetting previous task information. Okay. So let me just very quickly show you basically a glossary of Bayesian deep learning methods. Today we talk about variational inference, and with a bunch of different Q distributions. But definitely for deterministic approximation methods, there are lots of other ideas. So Laplace methods, especially those Laplace methods using, say, low rank covariance matrix, and also things like this tangent kernel thing, right? So they are actually working quite well. There are some other methods related to moment matching. That is another class of method. Apart from these deterministic approximate inference methods, you can also do sampling. Although HMC Hamiltonian Monte Carlo is super expensive, there are some cheaper versions of MCMC called stochastic gradient MCMC, for which you can just think about it as sort of like gradient descent plus some properly scaled noise. If you want to promote diversity, particle-based inference can also help you to make sure that your different experts are sort of like diverse and different. So the third class, which is one of the things that we are very excited about, is called function-based inference, which really tries to think about how you can improve the uncertainty quality directly in the function output space. Because ultimately, what we care, right, is the uncertainty estimate in your output. We don't really care about, let's say, the uncertainty estimate in your weights directly. And even if you can visualize it, it might be difficult to understand and explain. So what we really care about is these kind of, say, sausage plot in the output space, which means for this class of methods, often people use ideas from, say, Gaussian process, neural tangent kernels, and also deep kernel learning to help. So lastly, someone in the audience mentioned about these ensemble methods. Indeed, the deep ensemble is a very, very strong baseline. So interesting enough, this paper, okay, also shows some interesting results showing that they try their best to run HMC, okay, to get some close to ground truth result. And then they compare a bunch of these inference methods, like Bayesian inference, and also deep ensembles, to HMC results. And surprisingly, they found that the deep ensemble result is actually closer to the HMC result compared to the Bayesian inference results. So this again tells you that the quality of approximate inference is actually very key in terms of the performance of Bayesian neural network. So the theoretical framework of Bayesian neural network is not that difficult. Most of the efforts in this field, are spent on fast and accurate computation of the approximate theorem. Okay, so you might be interested in question about transformers, which is very new and still unclear. Okay, there are some observations here. So the first thing is that transformers needs a big amount of data to train. Okay, so for us, from our experience, that if you do, say, mean field variation inference, which can easily underfit, essentially it doesn't work that well in terms of transformers, because transformer itself already needs quite big amount of data to fit. So the other thing that people might be interested in is actually for transformers, right? The core module there is basically the multi-head attention. How do you actually going to apply these Bayesian neural methods in multi-head attention layers, right? So you can either apply these naive, these Bayesian neural methods like MC Dropout. Indeed, people have applied MC Dropout there, okay? Or there are people investigating this probabilistic version of attention, okay, and then try to come up with different versions of, say, probabilistic attention modules. So, there may be some other perspective, like for Gaussian process, which we've done some interesting work at this year's ICLEAR. So if you're interested, you can check it out. Okay, so in summary, let's just summarize some future directions, given that we don't have too much time. So today we spent some time to talk about, say, Bayesian neural networks, especially with a lot of focus on the regression task. Okay, so you probably have seen from the demo, right, that with a different initialization and also different methods, you can actually see different behaviors, right, of the outputs. So how would this sort of like the outputs, the distribution on F, Q of F, behave given a particular form of this weight space Q distribution? So that is an interesting question. Okay, then you can still ask the question, is weight space objective appropriate for mean field regression inference? Okay, or for Bayesian neural network in general. Okay. So another thing that I'm very interested in right now, and also we are doing quite a lot of research here, is basically how to scale up Bayesian neural networks in the area of foundation models when you have the number of parameters in the scale of billions. Okay, clearly you don't want to do sort of like any full convention method. Even like low rank convention methods it's just not going to work in terms of memory. Okay. So how can we actually make approximate procedure more efficient in both time and space complexity so that we can actually scale these things to, say, billions of parameters? That is still an active question and also the key question to be addressed in this field. So the other thing that we haven't touched today is basically prior. Okay. So for priors right now, we are basically just doing a mean field Gaussian prior, okay, in the weight space. How would these things induce a prior in function space? That is an interesting question. And from previous results, right, it's usually induced by the architecture. If you choose different architecture, in the function space, the behavior will be different. Especially if you have some inductive bias in your architecture, like ConvNet, this convolution, this kind of local thing, right? Then you will have some interesting prior in function space. But again, how to think about priors for transformer-based networks, that would be an interesting question because it has been shown that transformers have sort of like less inductive bias compared to methods like ConvNet. Okay. Yeah. Okay. We talk about some applications, but in general, for any applications that needs sort of like uncertainty or any applications that will involve in sequential decision making, right? So there is always room to improve the uncertainty estimate, and then think about how do you actually incorporate these, Bayesian neural networks, or in general, deep neural network with uncertainty estimates into your application pipeline. All right, yeah, thank you very much. So we are a little bit over time, so you can come and ask me questions now, but the solutions that are here, basically it's just the same, almost the same link, but you have this plus answer part.